characteristic equations and characteristic polynomials can be used to solve recurrence relations. In this video, we'll discuss what to do when the characteristic polynomials have repeated roots. Perhaps the most famous recurrence relation is the Fibonacci sequence, which says Fn equals Fn minus 1 plus Fn minus 2. Which together with the initial conditions, F0 equals 0 and F1 equals 1. This defines the Fibonacci sequence. But notice that this is precisely the type of recurrence relation on which we can use the characteristic root technique. And when you do, the only thing that changes is that the characteristic equation does not factor. So you need to use the quadratic formula to find the characteristic roots. In fact, doing so gives the third most famous irrational number, the golden ratio. Before leaving the characteristic root technique, we should think about what might happen when you solve the characteristic equation. We have an example from the previous video in which the characteristic polynomial has two distinct roots. These roots can be integers or perhaps irrational numbers requiring the quadratic formula to find them. In these cases, we know what the solution to the recurrence relation looks like. However, it is possible for the characteristic polynomial to have only one root. This can happen if the characteristic polynomial factors as x minus r squared. It is still the case that r to the n would be a solution to the recurrence relation, but we won't be able to find solutions for all initial conditions using the general form an, well, actually, I'll just write it out here so you guys can see. An equals ar1 to the n plus b r2 to the n. Did I write that? Yeah, r2 to the n. Since we cannot distinguish between r1 to the n and r2 to the n, this sort of problem is complex because our roots are the same here. We are in luck though, and this is what we're going to be discussing in this video. There is a technique for repeated roots. Suppose the recurrence relation an equals alpha an minus 1 plus beta an minus 2 has a characteristic polynomial with only one root r. Then the solution to the recurrence relation is an equals ar to the n plus b n r to the n. That n right there is new, it's unique, where a, b, and are constants determined by the initial conditions. Notice the extra n in b, n, r to the n. This allows us to solve for the constants a and b from the initial conditions. Let's look at an example on how we would do this. I'm going to set this up real quick by letting that big. All right, here's my example. Let's solve the recurrence relation. An equals 6an minus 1 minus 9an minus 2 with initial conditions a naught equals 1 and a1 equals 4. Okay? So the characteristic polynomial is x squared minus 6x, that's not an x, let's try that again, plus 9. We solve the characteristic equation x squared minus 6x plus 9 equals 0 to find our roots. By factoring, we get x minus 3 squared equals 0. So x equals 3. Is the only characteristic root. Therefore, we know that the solution to the recurrence relation has the form, I'm going to give myself just a little tiny bit more room here. We know that our answer is going to be of the form an equals a times 3 to the n plus b times n times 3 to the n for some constants a and b. Now use the initial conditions. We know that a naught equals 1, which is, if we plug n equals 0 into this right here, we get a times 3 to the 0 plus b times 0 times 3 to the 0. We also know that a1 equals 4, according to that right there. We have those two, which is also a times 3 to the 1 power plus b times 1 times 3 to the 1 power, because n is 1. So we know that this is just a, because 3 to the 0 is 1, and 0 times anything is 0, so that simplifies to a. And this second equation here simplifies to 3a plus 3b. So that right there says that a equals 1. And so because a equals 1 and 3a plus 3b equals 4, if a equals 1, that means 3 times a plus 3 times b equals 4 by that second equation there, which means that 3b equals 1, or that b equals 1/3. All right, therefore, the solution to the recurrence relation is, I'm going to erase some stuff here. an equals, there we go. an equals 1 times 3 to the n plus 1/3 times n times 3 to the n. Although we will not consider examples more complicated than these, this characteristic root technique can be applied to much more complicated recurrence relations. For example, if we have, let me actually just erase all this so I can, there we go. So for example, let's say we had an equals 2an minus 1 plus an minus 2 minus 3n minus 3. This has a characteristic polynomial x cubed minus 2x squared minus x plus 3. Assuming you see how to factor such a degree 3 or more polynomial, you can easily find the characteristic roots and as such solve the recurrence relation. The solution, by the way, would look like something like an equals ar1 to the n plus br2 to the n plus cr3 to the n. If there were 3 distinct roots. It is also possible that the characteristic roots are complex numbers, and those are really complicated because, well, I mean, the problems for these recurrence relations can get dramatically hard, dramatically fast, but typically in a discrete math course, this would be as far as you would need to go, where all the roots are distinct, or you might have a repeated root case. Anyways, thanks everyone, and I'll see you in the next video.